Alright, so in this video we're talking about potential energy diagrams. In the last video we talked a little bit about the activation energy. The activation energy is the energy needed to make the reaction go, to start the reaction. So the energy required to start the reaction. Okay, the activated complex is an intermediate step, an intermediate product between the actual reactants and the products. It's very unstable and only lasts for a few seconds in most cases. Okay, so a potential energy diagram has a general shape like so. Okay, where you have your energy of your reactants, the energy of your products. Okay, so we go from, our reaction progress goes from left to right. So we start with our reactants and we go to our products. Okay, and then of course on the y-axis we have our energy, usually in kilojoules. Okay. Now at the very top of the hill, that's our activated complex. Okay, and the distance between the reactants, right, and the top of the hill, that is our activation energy. And we learned that was symbolized as EA. We'll write that up here too so we can remember that's EA. Okay, and then we can also find the heat of our reaction by finding the difference. That's called delta H, the heat of our reaction. That's the heat of the reaction. And that is by taking the product's energy and subtracting the reactant's energy. Okay? Now, we can tell if this is exothermic or endothermic from the graph. So if our products are down here, right, that's a lower energy than our reactants, and we take products minus reactants. So in other words, we take a small number minus a large number, and we're going to get a negative value, right? And so a negative delta H, right, means that it is exothermic. And we've talked about that before, right? So for endothermic, we would have to have a positive delta H. And the graph then would change. For endothermic, it would change and look where the reactants are lower in energy than the products. So it would look more like that. Alright, so let's look at some example problems and questions we might see on this. So which letter represents the activation energy for the forward direction? Now when it refers to the forward direction, that means from reactants to products. Okay, proceeding in the forward direction. So we look here and we find a difference, right? We see the difference between the reactants and the top of the hill. So we find that value, right? And that is letter A right here. Okay. What is the value of the activation energy? Well, the reactant energy starts off here, right? And then the energy of activation is up here, right? And so we have 1, 2, 3, 4, 5. So 100 is divided up into 5, so those are 20s, right? So that's 120 here. Up here we have 220, 40, 60, 80. So the difference here between 280 and 120 gives us our activation energy because it's this distance here, right? And so that gives us 160 kilojoules. Okay, so what letter represents the delta H for the reaction? Well, delta H, as we just talked about a minute ago, is the difference between the reactant's energy and the product energy. So which one shows us the difference between reactants and products? So here's our reactants and here's our products, right? And the distance is right here, and that is letter B. Then it says, what is its value? So again, that's products minus the reactants. So we find the product energy, right? Is that right about here? So that's 220, 40, 60. So 260 minus the reactant's energy, which we said before was 120, and we get 140 kilojoules. Right? Now, is it endothermic or exothermic? Well, two ways we know that. Our delta H is positive, and our products are higher than our reactants. That makes it endothermic. Right? And then how would introducing a catalyst change the diagram? Well, in the previous lesson we learned that the catalyst lowers the activation energy. So when it does that, right, the way that is shown on the graph is that energy is just lower, right? The top of the hill becomes much less, right? So it lowers the activation energy, okay, which means it would lower the hill, if you will, right? Okay. So let's look at another example. Okay, diagram 2 here. Again, indicate this reaction is endothermic or exothermic and give the letter corresponding to delta H. So again, delta H is the difference between the reactants and the products. So our reactants this time are up here and our products are down here. Right? Here's our reactants and here's our products. Right, this time our products are lower than our reactants, right? And so that would make it exothermic. Energy was released, right? Because the products have less energy than the reactants. And the letter that corresponds to delta H is the one that's between R and P, right? Which would be this one here, and that would be the letter B. What is the effect on the diagram of increasing the concentration of the reactant? So we increase the concentration of the reactant. Is that going to change anything about this diagram? Does this diagram have anything to do with the concentration? No, it does not. Okay, so it would have no effect, right? But what is the effect on the rate of reaction, right? It would increase the rate. Okay. Which letter represents the position of the activated complex? Again, the activated complex is right up here at the top of the hill, and that is this little letter B. Right? What is the energy of the activated complex? Okay, so the activated complex is here. How much energy is it? These are, let's see, 25 increments, so this would be 175 kilojoules. Okay. And how would introducing a catalyst change the diagram? Again, it would lower the activation energy, okay, which means it lowers the hill. So if I were to draw that on here, right, I would have a lower hill, like so. Right. And that concludes this lesson.